Hello, everyone. What we're going to do in this video is prove and we'll talk about Chebychev's inequality, a nice consequence of this that's on the latest prelim, and prove and state the really foundational Fatou's lemma. Okay. So to prove Fatou's lemma, we're going to need Chebychev's inequality. So what is Chebychev's inequality? Uh, It's actually very similar to the probability inequality that most of us probably know. Sorry, not theorem, but inequality. Okay, so it's a very straightforward inequality. Let's say, as always, E is going to be measurable throughout this lecture. So let's say we have a measurable function, non-negative. If lambda is bigger than 0, then the measure of this set here, set of all x and e, where f of x greater than lambda is less than or equal to 1 over lambda times the integral of f over e. So, yeah, I will do this same way the book does. The kind of in the I think it's like page 387 or something like that. Where it does this towards the end. And really you can prove this just using the definition of this integral here. So what's the proof? As typical of any proof of Chebychev's theorem, let's give this a name. Sorry, bigger than lambda. Okay, so let's pick a very, very, very simple function. Particularly just lambda times the characteristic function of E lambda. Okay, and we're going to consider this as a characteristic function over E. Okay. So I claim that clearly lambda is positive, so this here is non-negative, but I claim it's less than or equal to f. Okay, so how do I prove that it's less than or equal to f? Well, we just look at two cases. Let's assume yeah, sorry. Yeah, so let's assume brain fart there. Let's assume x is in E lambda. Well, then just definition, characteristic function. This is lambda, and this is less than f of x, where we're using the fact that here we're using the fact that x is in E lambda instead of all x and E, where f of x is less than, sorry, f of x is bigger than lambda. Okay. And, well, trivially, if x is an E, take away E lambda, then, well, this is 0. Oops. All right, so if you recall the definition of the Lebesgue integral of a non-negative measurable function, this is very useful. So the conclusion is that this is between 0 and f on E, and in particular also this is a simple function. So I'll just remind you of the definition, the integral of f over E. Okay, so remember these two dots mean the definition. And I'll use this var phi tilde, because I want to particularly use this phi here. So this is a premium of all these integrals, or integrals of simple functions between 0 and f on E. All right. Okay, well, yeah, soup is, well, an upper bound of all of these integrals, so we have a particular integral in mind, integrating var phi here, what we described a moment ago, right here. Okay, so yeah, as an upper bound, this is bigger or equal to well, this is just lambda times this characteristic function. So that's going to just be lambda times the measure of lambda. And well, that proves it. The measure of E lambda is less than or equal to 1 over lambda times this integral here. So a nice little easy proof. All right, so a nice consequence of this is actually a prelim problem from the latest prelim, or either the latest or June 2023, forget which. But yeah, a very straightforward application. An example of how to use Chebychev's theorem is as follows. So a little proposition here. Yeah, so if I have a measurable non-negative function, of course, E is measurable, F is measurable also. So if this satisfies this integral equals 0, maybe make it a little clearer, then f of x particularly equals 0. The best we can say is for almost every x. All right. Okay, so the proof is very easy. Okay. Let's look at this set here. Set of all x, where f of x is positive. Okay. We want to prove that this has measure 0. So then f of x will be 0 for almost every x. The set of all x where this here is false has measure 0. This is a set right here that I'm putting in blue. This is a set of all x where this, what I haven't read, is false. So we got to prove that this has measure 0. And that's pretty easy. So we can't use Chebychev's theorem with lambda 0, unfortunately. But we do the next best thing. And do the obvious kind of next thing. Well, f of x is bigger than 0 precisely when f of x is bigger than 1 over n for some natural number n. Okay. And we use Chebychev's theorem on each of these. So this is kind of trivial here. So sorry, I need the measure of this. Okay, so these sets are equal, so obviously the measures are equal. And f is assumed to be measurable, so this is the countable union of measurable sets. Right. So actually these are going to be nested. These are, sorry, ascending. They're definitely ascending. In particular, if f of x is bigger than 1 over n, then it's certainly bigger than 1 over n plus 1, bigger than 1 over n plus 2, etc., etc. So these sets are getting bigger and bigger and bigger. Or you can use countable subadditivity, really doesn't matter which one you use. Well, I'll just use, because we do get equality. By continuity of measure, this is equal to this limit here. And now we will use Chebychev's inequality. Sorry. I'll use n, that it matters, but okay. So now we use Chebychev's inequality. So this is less than or equal to 1 over n integral e of f. Now, of course, 1 over 1 over is n. That could be very large. Sorry, I forgot the limit. But our assumption is that this right here is 0, right? So very simply, this is n times 0. It's a little funky, so I'll just do x here. X for multiplication. Well, that's 0. And that basically, however you write it. So these two brackets, doesn't matter. It's looks like no, but whatever. N times 0 equals 0. And that's it. There's really not much more to it than that. Yeah, so nice little application of Chebychev's inequality. All right, a much more useful not useful, but a much more interesting application is this Fatou. The way it's stated in the book is a little bit different than it usually is stated. I'll just prove this and then state what Fatou's lemma usually means. It's a very, very, very easy consequence of what the book states and what I'm about to prove. Okay, so what is Fatou's lemma? It states the following. They have a sequence of functions. So let's assume each of these is measurable. E, of course, is measurable. Now let's assume we have Fn converges to F pointwise almost everywhere on E. So Fn of X converges pointwise to F of X for almost every X in E. Okay. So the conclusion is that this is less than or equal to the lim inf of the integral of the Fn's. Okay. So ideally, we would like the integral of Fn to converge to F. Unfortunately, that often just doesn't happen. So maybe before proving Fatou's lemma, an example to show just that. I'll erase this in a minute. Let's say Fn equals 1 over n on R. So it's a constant on R. Trivially, well, for each one of these integrals, you're integrating 1 over n on the real line, and that's infinity. Really not much to that. By definition, this is going to be 0. So yeah, you don't in general get this, but you know, you do. I mean, this definitely shows you get Chebychev's inequality. Sorry, Fatou's lemma, this inequality here. In this case, the integral of f is 0, and the limit of the integrals is infinity. So 0 is less than infinity. It's trivial. Okay. Yeah, so we're going to investigate in general kind of interchanging limits and integrals. This is a really, really baby example to illustrate. In general, you just can't willy-nilly do that. You just can't. So this is going to be kind of the foundational result of when you can interchange limits and integrals. Okay, so it's got a nice proof. So proof of Fatou's lemma. A little bit technical, but yeah, it's a clever proof. It's a very clever proof using continuity of measure. Okay. So without loss of generality, assume that we have pointwise convergence on E. And I can do that because well, I just otherwise exercise a set of measure 0. So we know this is true for almost all X and E. Excision, excising a set of measure 0. We can assume we have this for all X and E. Okay. So I claim that it's enough to show, ETS for enough to show. And I'll go through the details. They're kind of trivial, but that's fine. It's enough to show that the following is true. Okay, the integral over all simple functions, var phi or whatever this is, I think it's var phi, is less than or equal to the lim of these integrals, where as usual, this is simple, and is between 0 and f. Okay. So let me call this quantity here star, so I don't have to keep writing it. Yeah, this is by definition. If true, then this integral here is primum of all these. Where these are simple. Okay, so what does that mean? That means that this quantity here is an upper bound for all these integrals over all these simple functions that are between 0 and f. Let me call this I. This whole set here, I for the set of all these integrals over simple functions. So this is an upper bound, I. Well, soup is the least upper bound. So this is soup of I. So we get what we need. And this is important to be able to look at simple functions. So yeah, this is our goal here for all these simple functions. All right, so I divide this up into, well, 3 cases. I'm not even going to call it a case. First, if this is 0, well, then we're done. So what am I doing? Sorry, I'm picking one of these simple functions. I want to look at this integral here. Rather, I want to look at this integral here, where we pick one of these simple functions. If this integral is 0, well, 0 is less than or equal to something non-negative. It's 0. So there's nothing to do. All right, so let's assume the integral is not 0. So easy case is the integral is 0. So we're going to show that the integral also is sorry. So this is going to be infinity. This doesn't make sense. So basically, we're going to show both sides are infinity in this case. Okay. Yeah, this is not too bad. So if this is true, then I can clearly pick some subset of E that has infinite measure and where this here is positive. The particular, it's a simple function, so it can only take on a finite number of numbers. Finite number of non-negative numbers. So we can pick we can pick this to be positive. And if we can't find E infinity and of course this is measurable, E infinity. We can't find A and E infinity, then, well, clearly, then this integral is finite. Okay. Yeah, if we can't find a positive A where the simple function is A on some set of infinite measure, then the function is positive on only sets of finite measure. And henceforth, the integral is finite. So kind of trivial there. Okay, so yeah, so we define some clever sets and use continuity of measure. So we know that F is the limit of Fn as n goes to infinity. So we don't want to strictly work with A. We want to work with anything smaller than A, but so A over 2 works. So let's define An in this following way. So this is admittedly a little tough to motivate. It's just kind of you go back and like, okay, well, this works, but why would I choose this in the first place? A little hard to describe, but so I want to settle x where fk of x is bigger or equal to a over 2 for all k bigger or equal to a. Okay, so clearly this is ascending. If x is an an, then clearly x is an an plus 1, because being an an means fk of x is bigger or equal to a over 2 for all k bigger or equal to n. Well, if it's true for all bigger or equal to n, it's true for all bigger or equal to n plus 1. It's kind of trivial. So these are definitely ascending. Maybe just make this a little neater. But okay, much nicer. All right, so by continuity of measure, we have that this limit is the measure of the union of the ans. Okay. Now, how does this help us? Okay, well, so A is var phi of x. And that's less than or equal to f of x on E. Sorry, on E infinity. So what does this tell me? Well, this is the limit. Yeah, sorry. So f of x, sorry, is the limit as n goes to infinity of fn of x. And well, f of x is bigger or equal to a. So that means this limit here, and this is kind of what's important, this limit here is bigger or equal to a. So definition of limit, there exists n where for bigger than n, then fk of x is bigger or equal to a over 2. That implies x is in an. And the point is, as x varies, well, you might have different n's. Well, just take the union. So that means x is in an. Okay, so in other words, E infinity is a subset of this union. This goes in the exact direction I want, because this has infinite measure. So infinity is going to be the measure of the set. That's less than or equal to the measure of the union. I don't per se care about that, but we had by continuity of measure, this is equal to the limit, and that's what I want. I want this limit to be to have infinite measure. Okay. All right. Sorry. There is no en, it's an. Okay, so how do we get so how do we get that this limit? Well, this is infinity. So actually we're actually going to show the limit is infinity. Not necessarily I mean, the limit is a limit, but we'll show that the limit is infinity. Should have made that clear a little clear before. And now we're going to use Chebychev's inequality. Okay, so in particular, so I'll write this. This is kind of obvious. Yeah, so an is a subset of this here. Why is that? It's pretty obvious. So if x is an an, where's the definition? If x is an an, then this is true for all k bigger or equal to n. In particular, it's true for n. N is bigger or equal to n. So if x is an an, then fn of x is bigger or equal to a over 2. Okay? So if x is an an, then fn of x is bigger or equal to a over 2. Okay. All right, so what does this say? This says that this is less than or equal to, by Chebychev's inequality, um 2 over a, and a could be really small, so this could be huge, but that doesn't matter. That's fine. So it's e integral fn. Right, so infinity is equal to this limit. Okay, well, that's less than or equal to 2 over a times this limit here. Okay. So the conclusion is, well, this is positive. Okay, so multiply by a over 2 on both sides. We get exactly what we want. The limit fn is equal to infinity. So sorry, the lim inf the lim inf of the integral being infinity is equivalent to the limit of the integral is infinity. So they're the same thing, really. If you actually think about the definition of limits. Okay. So yeah, we've proved. If you have any doubts, double check that lim inf of this integral is infinity is the same thing as the limit itself being infinity.